Hey class, it's me, Mr. Morris, continuing this series on gas laws. We're doing some example problems involving Gay-Lussac's law, which is P1 over T1 equals P2 over T2. So let's look down here at the next example problem. A gas has a pressure of 699.0 millimeters of mercury. It's data. At 40.0 degrees Celsius, a little more data. What is the temperature at standard pressure? Okay, standard pressure is 1.00 atm. And if you were to look at the back of the periodic table, we want those units to match the units that are given in the problem. 1 atmosphere is 760 millimeters of mercury. I'm just going to put 0.0 because it matches the sig figs of the other pressure unit. So let's write down our variables. P1, T1, P2, T2. P1 is our initial pressure. Sounds like that's 699.0 millimeters of mercury. Okay, T1, 40.0 degrees Celsius. Ask yourself, what's the one thing we always have to check with temperature? Always have to check if it's in Kelvin. Since this is not, it's in Celsius, we need to add 273 to that. So if I add 273.0 to this number, I'm going to get 313.0 Kelvin. Okay, pressure 2, our second pressure is 760.0 millimeters of mercury. And then our second temperature is going to be, that's our unknown actually. What is it? What's our standard temperature? It didn't tell me, or what's our temperature at standard pressure. It didn't tell me what units to use, so I'm going to do the easiest thing. I'm going to just leave it in Kelvin. Let's solve for the problem. P1 over T1 equals P2 over T2. P1 is 699.0 over T1, 313.0. And I am being consistent with sig figs here because our significant figures rule for addition or subtraction is to keep the lowest number of significant decimal places. Okay, so I've got 1 decimal place in this. Well, I need to add 273. I'm still going to have 1 decimal place in my answer. It's just 0.0. Okay, so back to this. 699.0 over 313.0 equals P2 over T2. So that's going to be 760.0 over our unknown, which is T2. Cross multiply to solve for it. 699.0 T2 equals, let's do 313.0 times 760.0. We get some big, huge, crazy number. Just write it down. 237,880. Okay, we'll round to sig figs at the end. As usual, I'm not going to be picky about how many sig figs you round to as you go through the problem, as long as you keep at least the same amount as the lowest number of sig figs given in the problem. But the main thing is we just want to make sure at the end we round to 4 significant figures, because I've got 4 here, 4 here, 4 here, and then that's my unknown. All right, next step. T2 equals 237,880 divided by 699.0. Just to make it legible, I'm going to move that up here. T2 equals, let's do that, divide by 699.0, I get 340.3 Kelvin. All right, That's not really where you can read it, but there we go. 340.3 Kelvin. Let's go down to example number 3. A 30.0 liter sample of nitrogen gas inside a rigid metal container. This is really important keyword. That tells me the volume does not change. Rigid means volume doesn't change, so the only thing that can would be pressure and temperature. It's at 20 degrees Celsius, 20.0 degrees Celsius. It's placed inside an oven whose temperature is 50.0 degrees Celsius. The pressure inside the container at 20 degrees Celsius, so the pressure inside the container when it's at 20 degrees Celsius was 3.00 atmospheres. What's the pressure of the nitrogen after the temperature is increased? So I've got two temperatures, 20 degrees, 50 degrees. At 20 degrees, the pressure is 3 atmospheres. What's the pressure at 50 degrees? I also have this volume given. How do I know which numbers I'm using and which ones I'm not? Well, we got to think about what's changing. We're only using the numbers that are changing. The ones that stay the same, the ones that don't change, we can ignore them because they're constant. They cancel each other out if you look at the equation. This one, 30.0 liters, that's volume. If it's a rigid metal container, that means the volume does not change. Since 30.0 liters is not going to change, we cross it out because it's constant. Now we can set up our equation. P1, T1, P2, T2. Write out our variables before we get started. P1 is at 20 degrees Celsius, which is our first temperature. Pressure is 3.00 atmospheres. T1, 20.0 degrees Celsius. P2, that's what I'm looking for. What is that? What's our pressure? T2, 50.0 degrees Celsius. Don't forget, when we're dealing with temperatures, you always add 273. I know I've been saying that every time I come to this, but it's important that you remember it. We add 273, so I get 293.0 Kelvin. And then if I add 50, you can get 323.0 Kelvin. All right, and then we can solve on the other side of this line. P1 over T1 equals P2 over T2. That's how we're going to write this out, and this is P1. So I'm going to do 3.00 over 293.0 equals P2 over 323.0. All right, so I have 3 times 323. I get 969. It's 969.0 or so on. It's exactly 969. Since I have 3 sig figs here, I'm just going to leave it like that. And then this is going to be 293.0 P2. That's a 9 there. Okay. If I want to solve for P2, P2 equals 969 divided by 293.0. You get to 3 significant figures, 3.31. P2 equals 3.31. And our units for pressure, it was 3 atmospheres, so our pressure units here are also going to be atmospheres. Hope that was helpful. Just the last 2 example problems from our Gay-Lussac's law notes. I'll see you in the next video on Avogadro's law.